Hello, am I audible?
Yes, sir.
So let us start this lecture. So let us start this lecture. So we shall discuss in this class we shall discuss isomorphic lattices and moreover the sublattices. Okay, so isomorphic lattices and sublattices. So so isomorphic lattices and and sublattices. Okay, so 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 the word isomorphism is same as in case of other structures, algebraic structures you can say. So we have definition. So two lattices two lattices L1 and L2 are isomorphic. Two lattices L1 and L2 are isomorphic if there is a bijection, there is a bijection alpha from L1 to L2, if there is a bijection alpha from L1 to L2 such that for every pair of elements, for every A and B in L1 the following two equations hold. The following two equations the following two equations hold. So first equation is that alpha of A join B is same as alpha A join alpha B, means this alpha preserves the operation of join, and alpha of A meet B A meet B, alpha of A meet B, it should be same as alpha of A meet alpha of B. So this is that this the meaning of isomorphism is actually a bijection map which preserves the lattice operation, that is both meet and join. Such a such a morphism alpha is called as, So such a morphism alpha is called an isomorphism. An isomorphism. So such a morphism alpha is called as an isomorphism. Okay. And then we have a observation which says that, so this is an observation, alpha from L1 to L2 is an isomorphism implies alpha inverse from L2 to L1 is an isomorphism. And suppose you have, and if beta from say another say from L2 to another lattice L3 is an isomorphism, then if I compose beta and alpha, then this beta composition alpha from L1 to L3 is an isomorphism, is an isomorphism. So this is an observation regarding isomorphisms. Okay, so it is straightforward, simple. So just let us see the proof of this one. So proof. So let you have say say B1 and B2, they belong to L2, be such that alpha inverse of say B1 equal to A1 and alpha inverse B2 equal to A2. Now since alpha is a bijection, so alpha inverse is also a bijection. So since alpha and alpha inverse are bijections, so this implies you have alpha of, so alpha inverse B1 is A1, so alpha of A1 should be B1 and alpha of A2 should be B2. Now if I take alpha inverse of B1 join B2, now I can replace it by alpha inverse of alpha A1 join alpha A2. Now since alpha is an isomorphism, so it preserves the join, so it is alpha inverse of alpha of A1 join A2. So which is equal to alpha inverse composition alpha of A1 join A2. So alpha inverse composition alpha is identity, so it is A1 join A2. Now A1 is your alpha inverse B1. So this is equal to alpha inverse B1 join alpha inverse B2. So this means alpha inverse preserves the join operation. So similarly, you can see that alpha inverse also preserves the meet operation. Alpha inverse of B1 B1 meet B2 equals alpha inverse B1 meet alpha inverse B2. Okay. So therefore the inverse of an lattice isomorphism is again in lattice isomorphism. Now the other fact, the other now since beta is an isomorphism, is an isomorphism. So you have you have if I take if I take beta of this one alpha of a1 join alpha of a2, okay, or in other words, that is to say that I am taking beta composition alpha of a1 join a2. So since alpha, first I will use the fact that alpha is an isomorphism. So alpha of a1 join alpha of a2. So then again, since beta is an isomorphism, so it is equal to beta of alpha of a1 join beta of alpha of a2. So this is equal to beta composition alpha of a1 join beta composition alpha of a2. So similarly, beta composition alpha of a1 meet a2 is again same as meet beta composition alpha of a2. So therefore the inverse of a lattice isomorphism is again a lattice isomorphism, and the composition of two lattice isomorphisms is again a lattice isomorphism. Now, since we have given an alternate characterization of a lattice in terms of partially ordered sets, so one can reformulate the definition of isomorphism in terms of the corresponding order relations. So now we reformulate the definition of isomorphism in terms of the corresponding order relations. Corresponding order relations. So then first I have to define what do we mean by a, a, a map between two partially ordered sets. Means what are, so definition, first I will give a definition. So first I will give a definition. So if so I am facing actually a problem in this my writing tab. So if P1 and P2 are two posets, two posets and alpha and alpha from P1 to P2 is a mapping. We say alpha is order preserving. We say alpha is order preserving if alpha a1 less than or equal to alpha a2 holds in P2 whenever a1 less than or equal to a2 holds in P1. Okay, so such mappings, they are called as order preserving mappings or monotone mappings between any two posets. Now we will prove a result which actually links the notion of isomorphisms in terms of meat and giant and in terms of these order preserving mappings. So this is in fact a theorem that we are going to prove. So we have a theorem. So this is the theorem which we are going to prove. So this is the theorem. Two lattices. So just 1 minute. So we will prove this theorem. Just wait a while. So this is the theorem. So I will restart this class. So I request all of you to rejoin because there is might be some problem in this writing device.